In this video, we'll guide you through the fundamentals of data structures and algorithms in C++ step by step. Join us as we explain the concepts, provide in-depth code explanations, and demonstrate practical implementations. Whether you're a beginner or need a refresher, this video will give you a solid foundation to excel in coding interviews and real-world applications. Understanding these concepts is crucial for any aspiring programmer, as they form the building blocks for efficient problem solving and software development. Now, before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm, and with that out the way, let's hop right into it. Now, before we jump into coding, let's discuss some essential concepts. Data structures are containers that allow us to store and organize data effectively, while algorithms are step-by-step procedures for solving problems efficiently. The choice of data structure and algorithm can significantly impact the performance of our programs. We'll begin with an array, a simple and commonly used data structure. In this code snippet, we start by including the necessary header file iostream, which provides input and output operations. Inside the main function, we declare an array called array with a size of 5 and initialize it with the values 1, 2, 3, 4, and 5. To access these elements in the array, we use the index notation. For example, array2 refers to the element at index 2, which is the third element in the array. Now, you must remember that array indices start at 0, so 1 would be 0, it would be 0, 1, 2, 3, 4. We output the value with the std_cout. Next, we modify an element in the array by assigning a new value to it. In this case, we set array3 to 10. We again use std_cout to display the modified element. To traverse the array and print all of its elements, we use a for loop. The loop variable I starts at 0 and iterates until it reaches 4, which is the last valid index in the array. Within the loop, we output each element followed by a space. Finally, we end the line with std and 1l. Alright, moving on, let's explore another popular data structure, which is linked lists. In this code, we first include the iostream header file for input and output operations. Then we define a structure called node, which represents a single node in a linked list. Each node contains an integer data value and a pointer to the next node, denoted by node, next, node, here, next. Inside the main function, we declare 3 pointers, head, second, and third, which will point to the nodes of our linked list. To create nodes, we allocate memory using the new keyword and assign the addresses to our pointers. In this case, we create 3 nodes, head, second, and third, and next, we assign data values and link the nodes together. We set head data to 1, and head next to the address of second, indicating that the next node after head is second. We similarly assign values and link the remaining nodes. To traverse a linked list and print its data values, we use a while loop. We start by initializing a pointer, current to head, as long as current is not a null pointer, indicating that it would be the end of the list. We output the data value of the current node using std_cout. Then we update current to point to the next node, current, next, and continue the loop. Finally, we end the line with std_end. Alright, and that's going to conclude our introduction to data structures and algorithms in C++. We covered arrays and linked lists, which are 2 fundamental building blocks of programming. If you guys enjoyed or found this video helpful, drop a like, subscribe for more videos, and we'll catch you in the next one. Now, we're going to talk about arrays and dynamic arrays in C++. Now, before we dive into the coding, let's understand the concepts of arrays and dynamic arrays. An array is a fixed-size collection of elements of the same data type, while dynamic arrays allow us to allocate memory dynamically at runtime. They provide flexibility and the ability to resize the array as needed. We'll begin by exploring the implementation of arrays in C++. In this code snippet, we include the IOStream header file for input and output operations. Inside the main function, we declare an array called numbers with a size of 5 and initialize it with the values 1, 2, 3, 4, and 5. And then to access the arrays, we use the index notation. We can modify an element in the array by assigning a new value to it. And to traverse the array and print out all of its elements, we use a for loop. Alright, so that should have been review. Now let's move on to dynamic arrays, which provide the ability to allocate memory dynamically at runtime. In this code, we declare a variable size to store the desired size of the dynamic array. We prompt the user to enter the size using the std cin and store it in size. Next, we use the new keyword to dynamically allocate memory for the dynamic array. We declare a pointer called dynamic array of type int and assign the memory address returned by new int size to it. This allocates memory for an array of integers with the specified size. We then initialize the elements of the dynamic array using a loop. Each element is set to its respective index plus 1. To access and modify elements of the dynamic array, we follow the same indexing rules as with regular arrays. We output the elements at index 2 and modify the element at index 3. To traverse and print all the elements of the dynamic array, we use another loop. Similar to the array implementation, the loop variable I starts at 0 and iterates until it reaches size -1. We output each element followed by a space. Finally, we deallocate the dynamically allocated memory using delete dynamic array. This frees the memory back into the system. Now we're going to talk about stacks and queues in C++. Now before we delve into coding, let's understand the concepts of stacks and queues. A stack follows the last in, first out principle, or LIFO, where the last element inserted is the first one to be removed. On the other hand, a queue follows the first in, first out principle, where the first element inserted is the first one to be removed. Let's start with the implementation of a stack in C++. In this code snippet, we include the IOStream and stack header files. The stack header file provides the necessary functionalities for implementing a stack. Now, inside the main function, we create a stack called myStack using the std stack int syntax. To push elements into the stack, we use the push function. In this case, we push the integers 1, 2, 3, 4, and 5 onto the stack. To access the top element of the stack, we use the top function. We output this using std cout. To remove elements from the stack, we use the pop function. In this example, we pop 2 elements from the stack. To check if the stack is empty, we use the empty function. If the stack is empty, we output stack is empty. Otherwise, we output stack is not empty. Now, let's move on to the implementation of a queue in C++. In this code, we include the IOStream and queue header files. The queue header file provides the necessary functionalities for implementing a queue. Inside the main function, we create a queue called myQueue using the std queue_int syntax. To enqueue elements into the queue, we use the push function. In this case, we enqueue the integers 1, 2, 3, 4, and 5. To access the front element of the queue, the element that would be dequeued next, we use the front function. We output this element using std cout. To remove elements from the queue, we use the pop function. In this example, we dequeue 2 elements from the queue. To check if the queue is empty, we use the empty function. If the queue is empty, we output queue is empty. Otherwise, we output queue is not empty. Now, let's talk about graph and graph traversals in C++. Before we start coding, let's understand the concepts of graphs and graph traversals. A graph consists of nodes, or vertices, and edges that connect these nodes. Graph traversals help us explore and analyze the connectivity within a graph. Two common graph traversal algorithms are depth first search, DFS, and breadth first search, BFS. Let's begin by implementing a graph in C++. In this code snippet, we include the IOStream and vector header files. The vector header file provides a dynamic array-like container which we'll use to represent our graph's adjacency list. Next, we define a class called graph. Inside the class, we have a private member variable numVertices to store the number of vertices in the graph. We also have an std vector called adjacency list to represent the graph's adjacency list. The graph constructor takes the number of vertices as an argument and resizes the adjacency list vector accordingly. To add an edge between two vertices, we use the addEdge function. In this example, we add edges between various vertices by updating the adjacency list accordingly. To print the graph, we use the printGraph function. It iterates through each vertex and its neighbors in the adjacency list, outputting the vertex and its adjacent vertices. Now, let's move on to graph traversals using the depth first search and breadth first search BFS algorithms. And this code will be pasted in the description so you can follow along on Replit or your IDE of choice. In this code, we continue with the graph class definition and the necessary header inclusions. We define two member functions, depth first search and breadth first search. The depth first search function performs depth first search traversal. It uses a stack to keep track of the vertices to visit. We initialize a Boolean vector visited to keep track of visited vertices starting from the specified start vertex. We push it onto the stack, mark it as visited, and continue until the stack is empty. In each iteration, we pop a vertex from the stack, output its value, and push its unvisited neighbors onto the stack. The breadth first search, or BFS, function performs BFS traversal. It uses a queue instead of a stack. Starting from the specified start vertex, we first enqueue it, mark it as visited, and then continue until the queue is empty. In each iteration, we dequeue a vertex from the queue, output its value, and enqueue its unvisited neighbors. In the main function, after creating the graph and adding edges, we demonstrate graph traversal using both DFS and BFS algorithms. We output the visited vertices during the traversal. Now, we're going to talk about hash tables and hashing in C++. Now, before we dive into the coding, let's understand the concepts of hash tables and hashing. A hash table, also known as a hash map, is a data structure that uses a hash function to map keys to values. This allows for constant time average case data retrieval. Hashing involves converting data into a numerical value hash code using a hash function. Let's begin by implementing a hash table in C++ using the standard template library, stl. In this code snippet, we include the IOStream and unordered map header files. The unordered map header file provides the necessary functionalities for implementing a hash table. Inside the main function, we create a hash table called myHashTable using the std unordered map int std string syntax, or this right here. This hash table associates integer keys with string values. To insert key value pairs into the hash table, we use the insert function. In this example, we insert 4 key value pairs using brace and closed initializer lists. To access and modify values in the hash table, we use the square bracket notation. We output the value at key 2 using std_cout and modify the value at key 3. To check if a key exists in the hash table, we use the count function. If the count of a key is greater than 0, it means that the key exists in the hash table. To remove a key value pair from a hash table, we use the erase function. In this example, we remove the key value pair with key 2. To print the hash table, we use a range-based for loop. We iterate over each key value pair in the hash table and output the key and value using std_cout. Now, let's explore the concept of a hash function, which plays a crucial role in hashing. In this code, we include the IO stream and functional header files. The functional header file provides the hash template class, which we'll use for our hash function. Inside the main function, we create a hash function using the std hash std string syntax. This hash function is specialized for strings. To compute the hash value of a data element, we call the hash function with the data as the argument. In this value, we compute the hash value for the string hello world and store it in the hash value variable. We then output the hash value using std_cout. Now we're going to talk about heaps and priority queues in C++. Now, before we start coding, let's understand the concepts of heaps and priority queues. A heap is a complete binary tree that satisfies the heap property, where the value of each node is either greater than or equal to in a max heap, or less than or equal to in a minimum heap, the values of its children. Priority queues are abstract data types that provide efficient access to the highest or lowest priority element. Let's begin by implementing a heap in C++ using the standard template library or STL. In this code snippet, we include the IO stream, vector, and algorithm header files. The vector header file provides a dynamic array-like container, and the algorithm header file provides functions to manipulate the vector. Inside the main function, we create a vector called maxHeap and initialize it with elements. To convert the vector into a max heap, we use the makeHeap function. This function reorganizes the elements in the vector to satisfy the heap property. To insert an element into the max heap, we use the pushback function to add the element to the vector, and then we use the pushHeap function to adjust the heap structure accordingly. To remove the maximum element from the max heap, we use the popHeap function to move the maximum element to the end of the vector, and then we use the popBack function to remove it. To sort the max heap in descending order, we use the sortHeap function along with the std_int comparator. This sorts the elements in vector in descending order, satisfying the heap property. And finally, we print out the elements of the max heap using the range-based for loop and the std_cout. Now let's explore the implementation of a priority queue using STL. In this code, we include the IO stream and queue header files. The queue header file provides the necessary functionalities for implementing a priority queue. Inside the main function, we create a priority queue called max priority queue using the std priority queue int syntax. By default, it's a max heap based priority queue. To insert elements into the priority queue, we use the push function. In this example, we push several elements into the priority queue. To access the top element of the priority queue, or the element with the highest priority, we use the top function. We output this element using std_cout. To remove the top element from the priority queue, we use the pop function. To check if the priority queue is empty, we use the empty function. If the priority queue is empty, we output priority queue is empty. Otherwise, we output priority queue is not empty. Now we're going to talk about sorting algorithms in C++, including bubble sort, selection sort, and insertion sort. Now, before we start coding, let's understand the concepts of bubble sort, selection sort, and insertion sort. These algorithms are comparison-based and work by repeatedly swapping or selecting elements until the data is sorted. Each algorithm has its own approach and efficiency characteristics. Let's begin by implementing bubble sort in C++. In this code snippet, we include the IO stream and vector header files. The vector header file provides a dynamic array-like container, and the IO stream header file enables input and output operations. We define a function called bubble sort that takes a reference to a vector as a parameter. This function implements the bubble sort algorithm. Inside the bubble sort function, we initialize a variable and with the size of the input array. We use two nested loops to iterate through the array and compare adjacent elements. If an element is greater than its adjacent element, we swap them using the std_swap function. In the main function, we create a vector called data and initialize it with unsorted elements. To sort the vector using bubble sort, we call the bubble sort function passing data as the argument. Finally, we print the sorted array using a range-based for loop and std_cout. Now, let's move on to implementing selection sort in C++. In this code, we include the IO stream and vector header files as before. We define a function called selection sort that takes a reference to a vector as a parameter. This function implements the selection sort algorithm. Inside the selection sort function, we initialize a variable n with the size of the input array. We use the two nested loops to iterate through the array and find the minimum element in the unsorted position. We then swap the minimum element with the first unsorted element using the std_swap function. In the main function, we create a vector called data and initialize it with unsorted elements. To sort the vector using selection sort, we call the selection sort function, passing data as the argument. Finally, we print the sorted array using range-based for loop and std_cout. Lastly, let's explore the implementation of insertion sort in C++. In this code, we include the IO stream and vector header files as before. We define a function called insertion sort that takes a reference to a vector as a parameter. This function implements the insertion sort algorithm. Inside the insertion sort function, we initialize a variable n with the size of the input array. We iterate through the array starting from the second element. For each element, we compare it with the element to its left and shift them to the right until we find the correct position for the element. We then insert the element at its correct position. In the main function, we create a vector called data and initialize it with the unsorted elements. To sort the vector using insertion sort, we call the insertion sort function, passing data as the argument. Finally, we print the sorted array using a range-based for loop and std_cout. Now we're going to talk about merge sort and quicksort in C++. Now, before we start coding, let's understand the concepts of merge sort and quicksort. Merge sort is a divide and conquer algorithm that recursively divides the array into smaller subarrays, sorts them, and then merges them back together. Quicksort is also a divide and conquer algorithm that partitions the array into two different subarrays, around a pivot element and recursively sorts the subarrays. Each algorithm has its own approach and efficiency characteristics. Let's begin by implementing merge sort in C++. And this entire code will be in the description so that you can follow along in Replit or your IDE of choice. In this code snippet, we include the IO stream and vector header files. The vector header file provides a dynamic array-like container, and the IO stream header file enables input and output operations. We define two functions, merge and merge sort. The merge function merges two sorted subarrays into a single sorted subarray. The merge sort function implements the merge sort algorithm. Inside the merge function, we initialize the variables n1 and n2 to store the sizes of the two subarrays. We create two additional vectors, left array and right array, to store the elements of the subarrays. We then copy the elements from the original array into the subarrays. Next, we perform the merging process by comparing elements from both subarrays and placing them in the correct order in the original array. In the merge sort function, down here, we recursively divide the array into smaller subarrays until the base case is reached. We then merge these subarrays back together using the merge function. In the main function, we create a vector called data and initialize it with unsorted elements. To sort the vector using merge sort, we call the merge sort down here function, passing data, the left index 0, and the right index data size -1 as arguments. And finally, we print the sorted array using a range-based for loop and std_cout. Now let's move on to implementing quicksort in C++. In this code, we include the IO stream and vector headers as before. At the bottom is just return 0. We define two functions, person and quicksort. The person function persons the array around a pivot element, placing smaller elements to the left and larger elements to the right. The quicksort function implements the quicksort algorithm. Inside the person function, we choose the last element as the pivot. We initialize the variable I to keep track of the smaller element's index. We iterate through the array, and if we find an element smaller than the pivot, we increment I and swap the elements. Finally, we swap the pivot element with the element at index I+1 to place the pivot in its correct position. In the quicksort function, we recursively partition the array and sort the subarrays around the pivot element. In the main function, we create a vector called data and initialize it with unsorted elements. To sort the vector using quicksort, we call the quicksort function, passing data, the left index 0, and the right index data size -1 as arguments. Finally, we print the sorted array using a range-based for loop and std_cout. Now we're going to talk about linear search and binary search in C++. Now before we start coding, let's understand the concepts of linear search and binary search. Linear search is a simple algorithm that iterates through each element in a collection and compares it with the target value until a match is found or the end of the collection is reached. Binary search, on the other hand, is a more efficient algorithm that requires the collection to be sorted. It repeatedly divides the collection in half and compares the middle element with the target value until a match is found or the collection is exhausted. Each algorithm has its own approach and efficiency characteristics. Let's begin by implementing linear search in C++. In this code snippet, we include the IO stream and vector header files. The vector header file provides a dynamic array-like container, and the IO stream header file enables input and output operations. We define a function called linear search that takes a constant reference to a vector and the target value as parameters. This function implements the linear search algorithm. Inside the linear search function, we use a for loop to iterate through each element of the array. We compare each element with the target value, and if a match is found, we return the index at which the target is found. In the main function, we create a vector called data and initialize it with elements. We also define a target value to search for. To search for the target value using linear search, we call the linear search function, passing data and the target value as arguments. Finally, we check the result returned by the search function. If the result is not -1, we output target found at index result. Otherwise, we output target not found in the array. Now let's move on to implementing binary search in C++. In this code, we include the IO stream and vector header files as before. We define a function called binary search that takes a constant reference to a vector and the target value as parameters. This function implements the binary search algorithm. Inside the binary search function, we initialize variables left and right to keep track of the leftmost and rightmost indices of the search range. We use a while loop to repeatedly divide the search range in half until the target is found or the search range is exhausted. We calculate the middle index, mid, and compare the element at mid with the target value. Based on the comparison, we update the search range by adjusting the left or right index. In the main function, we create a vector called data and initialize it with sorted elements. We also define a target value to search for. To search for the target value using binary search, we call the binary search function, passing data and the target value as arguments. Finally, we check the result returned by the search function. If the result is not -1, we output target found at index, which is the result. Otherwise, we output target not found in the array. Now we're going to talk about Dexters Algorithm, a popular algorithm for finding the shortest path in a graph. Before we start coding, let's understand the concepts behind Dexter's algorithm. Dexter's algorithm works on a weighted, directed, or undirected graphs. It maintains a priority queue of nodes and iteratively selects the node with the shortest distance from the source. The algorithm then updates the distances of neighboring nodes and continues until all of the nodes have been processed. The resulting distances represent the shortest paths from the source to all other nodes in the graph. Let's begin by implementing the graph class in C++. In this code segment, we define a graph class that encapsulates the functionality of our graph. It consists of a private member, addList, which is a vector of vectors representing our adjacency list. We also have a constructor to initialize the number of nodes and allocate space for the adjacency list. The addEdge function adds an edge to the graph by connecting a source node to a destination node with a given weight. We add edges in both directions since the graph is undirected. Now let's implement Dijkstra's algorithm within our graph class. In this code segment, we define Dijkstra's shortest path function within our graph class. This function implements Dijkstra's algorithm to find the shortest path from a given source node. We initialize a vector called distance with I and f representing infinity for all nodes except the source node, which is set to 0. We also initialize a priority queue, pq, to store nodes based on their distance. The algorithm iterates as long as the priority queue is not empty. It retrieves the node with the shortest distance, u, from the priority queue. Then, it explores all neighboring nodes of u and updates their distances if a shorter path is found. The updated nodes are pushed into the priority queue. Lastly, let's add some code to print the shortest distances from the source node. In this code segment, we add the code to print the shortest distance from the source node. We iterate over all the nodes and check if their distance is equal to INF. If not, we print the node's index and its distance. Otherwise, we print INF to represent that there is no path to that node from the source. Now, we're going to talk about topological sorting and strongly connected components in C++, which are two important concepts in graph theory. These concepts are widely used in various applications, such as task scheduling, dependency resolution, and cycle detection. Whether you're a beginner or looking to reinforce your knowledge, this comprehensive tutorial will provide you with a solid understanding of topological sorting and strongly connected components in the context of C++. Now, before we start coding, let's understand the concepts behind topological sorting and strongly connected components. Topological sorting is a linear ordering of the vertices of a directed graph, where for every directed edge uv, vertex u comes before v in the ordering. Strongly connected components are subsets of a directed graph in which there is a path between every pair of vertices. These concepts help us understand the structure and dependencies within a directed graph. Let's begin by implementing topological sorting in C++. And this code will be in the description if you want to follow along in your IDE or Replit. In this code snippet, we define a graph class that encapsulates the functionality of our directed graph. It has a private member addList, which is a vector of vectors representing the adjacency list, and then we have three member functions within the graph class. The constructor initializes the number of nodes and allocates space for the adjacency list. The addEdge function adds a directed edge from vertex u to vertex v in the adjacency list. The topological sort util function over here is a utility function used by topological sort here. It performs a DFS traversal, marking visited nodes and pushing them onto a stack. The topological sort function initializes a vector of visited nodes and a stack. It iterates through all nodes and calls topological sort util for unvisited nodes. Finally, it prints the topological sorting by popping elements from the stack. In the main function, we create a graph object called graph with 6 nodes. We add edges to the graph using addEdge, the addEdge function, specifying the source and destination of each edge. To perform topological sorting, we call the topological sort function on the graph object. Finally, we print the topological sorting by popping elements from the stack. Alright, so now let's move on to implementing strongly connected components in C++. And once again, this will all be in the description. So in this code segment, we continue working with the graph class. We add 2 member functions to the graph class. The DFS util function is a utility function used for DFS traversal. It marks visited nodes and prints them. The getTranspose function returns the transpose of the current graph by reversing all edges. The print strongly connected components function performs the Dexters algorithm for finding strongly connected components. It first fills the stack with the vertices in their finishing order based on DFS. Then it obtains the transpose of the graph, and finally it performs DFS on the transpose to print the strongly connected components. In the main function, we create a graph object called graph with 7 nodes. We add directed edges to the graph using the addEdge function, and then to find strongly connected components, we call the print strongly connected components function on the graph object. And finally, we print the strongly connected components. Now we're going to talk about AVL trees and red-black trees in C++. Now before we start coding, let's understand the concepts behind AVL trees and red-black trees. Both structures are binary search trees that maintain balance by performing rotations when necessary. AVL trees use height balance, ensuring that the difference in heights between left and right subtrees is at most 1. Red-black trees use color properties and perform rotations to maintain balance. These self-balancing properties enable efficient search, insertion, and deletion operations. Let's begin by implementing AVL trees in C++. And this entire code will be in the description if you want to follow along in Replit or your IDE of choice. In this code snippet, we define a class called AVL tree to encapsulate the functionality of our AVL tree. It consists of a struct called node, which represents a node in the AVL tree. Each node has a key value, height, and pointers to the left and right child nodes. The height function calculates the height of a node by returning 0 if the node is null, or the height stored in the node otherwise. The balance factor function calculates the balance factor of a node by subtracting the height of its right child from the height of its left child. The rotate left and rotate right functions perform left and right rotations, respectively, to balance the tree. The insert function recursively inserts a new key into the AVL tree while maintaining balance using rotations when necessary. The in-order traversal function performs an in-order traversal of the tree and prints the keys. In the main function, we create an AVL tree called AVL, and we insert several keys into the tree and then print out the in-order traversal. Alright, now let's move on to implementing red-black trees in C++. In this code segment, we define a class called red-black tree to encapsulate the functionality of our red-black tree. It consists of a struct called node, which represents a node in the red-black tree. Each node has a key value, color, either red or black, and pointers to the left, right, and parent nodes. Within the red-black tree class, we have several helper functions. The insert function recursively inserts a new key into the red-black tree while maintaining the properties of a red-black tree. It uses the fix violation function to handle classes where the red-black tree properties are violated. The fix violation function applies the necessary rotations and color changes to fix violations of the red-black tree properties. The rotate left and rotate right functions perform left and right rotations, and they maintain the red-black tree properties. The in-order traversal function performs an in-order traversal of the tree and prints the keys. In the main function, we create a red-black tree object called rbTree. We insert several keys into the tree and then print the in-order traversal. Now we're going to talk about the tree data structure in C++. It's a versatile tree-based data structure used for efficient string storage and retrieval. We'll introduce the concepts, guide you through the code line by line, and provide detailed explanations. Now, before we start coding, let's understand the concepts behind trees. A tree, also known as a prefix tree, the tree-based data structure that allows efficient retrieval of strings. It's particularly useful when dealing with a large number of strings as it provides fast search and insertion operations. Each node in a tree represents a character, and the path from the root to a node forms a string. Trees or tries are commonly used in applications like autocomplete, spell checkers, and IP routing tables. Let's begin by implementing the trie data structure in C++. In this code snippet, we define two classes, treeNode and tree. The treeNode class represents a node in the tree, and the tree class encapsulates the functionality of our trie data structure. The treeNode class has two members. The isEndOfWord Boolean variable indicates whether the node represents the end of a word. The children unordered map holds the child nodes, where the key is the character and the value is a pointer to the corresponding child trie node. The trie class has three member functions. The insert function inserts a word into the tree by traversing through the characters of the word and creating new nodes as needed. The search function searches for a complete word in the trie by traversing through the characters and checking if each character exists as a child node. The starts with function checks if a given prefix exists in the tree by traversing through the characters by verifying their presence. In the main function, we create a trie object called tree. We insert several words into the tree using the insert function. Then we demonstrate the search and starts with functions by performing searches and prefix checks. Finally, we print the results.